Oops. Nathan, can you tell me whether you can see this screen? Oh, can you see this screen?
Yep.
Okay. Okay. Good. Hello everyone. So we're gonna study the likelihood-based approach. Okay. So today we'll just before we move on to the missing data, we'll study the basic contents for the likelihood method with no missing data. So we have suppose you have n realization of random variable from a distribution P with density F, and this means the Ladon-Nikodym derivative, but you don't. It's not really a big deal. So we don't know the true density, right? F. So we assume a model. So the fact. So what I mean by that? Well, we assume that F belongs to a parametric family of densities. So parametric means that we use the parameter to characterize the density. So if you know the parameter, you know the density, basically, right? And the dimension of the parameter here is P, and P does not increase with the sample size. So some modern techniques, sometimes P increases with the sample size, semi-parametric or machine learning, deep learning. They in their problem, dimensional parameter increases with sample size. So that gives a more flexible modeling. But we'll for the beginning, we'll just focus on the parametric model for now. But maybe later we will move on to more advanced techniques too. So basically, true F as a function of Y is completely determined by zeta null. Okay, so that is the basic setup. And I guess if you, okay, let me quickly show you. I don't know whether you guys check the canvas. So in the canvas, I actually uploaded the script. The reason is that I usually forget something. So I just want to make sure that even though I missed something in the class, you can still find it in the script. So because probably you guys have different background, so maybe I may assume too much. So I may have a high expectation about you, and so may assume that you know something, right? And then start from there. But some of you may not have that background. Then I hope that you can at least figure out where to check, right? So for example, if you are not really familiar with parametric model, and then you can, later. So a lot of concepts are actually introduced, but I cannot really cover all the concepts from scratch, right? I have to start from somewhere. And I hope that my starting point is a good starting point for you, but that's not always the case, my experience. But I hope that, but feel free to let me know, right? Feel free to let me know and ask questions so that I can have a better understanding about your background, and then I can surely adjust it. Anyway, so likelihood is a basic tool for learning with a statistical model, and the idea is very simple: just to use the joint density as a function of zeta, and try to maximize with respect to zeta. So notice that you can see that I use red color for zeta, which means that zeta is unknown, and that has to be determined. And so, and y is actually vector, right? Vector of size n, so data, right? And so that means this is, the likelihood is actually a function of theta and data, right? Theta and data, but data is what we observe, and theta is unknown. And so then given the data is a function of theta only, right? As a function of unknown. If you are talking about what is a function of unknown, what is unknown, then the only thing unknown is theta. But also you can see that this is actually a function of random variables, right? So Ly, I mean the L theta has a y in it, and y is a random variable. So that means it follows some distribution, right? There's some mechanism, and that actually determines the statistical properties of the estimator later that we're going to study. So anyway, that is a likely function, and maximum likely estimator is essentially the maximizer of the likely function with respect to theta. Okay. So now our goal is to study minimum statistical properties of the maximum likely estimator. So what is the goal? So let me just move on to the goal first and then come back. So the goal is to at least understand what I mean by understand the property, the very basic property. The very basic property is that MLE converges in property to the true parameter. Okay, so that is the goal. And to go to, take a journey to that goal, we need to learn something. So one of the important concepts is model identifiability. So the model identifiability means that we should restrict our attention to a sensible class of models, right? So for example, if you, sorry about those who are in the, okay. So suppose I make my model like this. Normal theta 1 plus theta 2 and 1. Okay. And I'm interested in estimating theta 1 and theta 2. So is this sensible? Not really, right? I mean, because you cannot really uniquely determine theta 1 and theta 2 from the observation, no matter how much data you have, right? You are essentially, waste your energy if you focused on this wrong problem, right? So the idea is, this is really nonsense. So why don't we, discard this option as a problem set and focus on what is we can call as sensible, right? So the minimum condition we are going to discuss in the parametric model, in the statistical model, is that we are going to focus on identifiable models, right? And that is so this is the definition. So so this is actually about a class, right? So model is actually class of distribution, a certain class of distribution, and we want to determine a particular element in the class by determining theta, right? And so that means theta should be well defined, right? So as a function, so that means you don't. So this is actually you have a theta space and function space, and kind of map. Right, but what you don't want to, so that means what? This is one-to-one. So you don't, so if you have this, sorry, I shouldn't, same, right? If two different zeta refers to the same model, that's not good, because you want to completely determine a particular element in the probability space in terms of zeta, then it should be one-to-one, right? So as a function of zeta, it should be one-to-one. So basically, this is the basic idea. I mean, so the term may sound very complex, but the actual concept is not really that difficult. It's just if you view the model as a mapping from zeta to the distribution, it should be one-to-one in terms of zeta. Okay, and then there's some technical details. So how do I mean by, so when we talk about equal in terms of distribution, we should exclude the probability 0. I mean, so for example, F1, density F1 and F2 are equal or not equal. Well, it may look unequal, but actually it is unequal only at point x equal to 0 and 0 x equal to, actually x equal to 1, right? And which has a measure 0. So that's not really a problem. So we only cares as a function of x, that we only cares on the point with the positive measures. So that is the basic idea. Okay. So that is about identifiability. Okay. So on the identifiable model, we have a very interesting result. So the result is that this, the Q zeta. So the condition is the model class is identifiable and some moment exists. That basically means the Q zeta is a finite value. So the idea is, okay, so this is a function, right? So we just take the expectation of the log density. Okay, so expectation of a log density, then when that is actually this one. So you take the integral of the log density evaluated at the density, true density, right? So zeta null is the true density. Remember that zeta null is the, so we fix the, so zeta null is true parameter that we referring to about the random variable. So for fixed parameter, we can compute the integral, right, expectation. And then zeta is red one is unknown. I mean, we vary. And then if you view it as a function of zeta, it takes the maximum at zeta null. And that is unique. Okay. So, well, that, so we are going to rigorously prove this, but to prove this, we need a tool. We need to understand another concept, which is something called information Kolmogorov, Shannon Kolmogorov information, which is often called information inequality. But more importantly, we first need to introduce the Kullback-Leibler divergence measure. So Kullback-Leibler divergence measure is a very important concept in not just in the statistics, actually in many areas, in signal processing and all computer science, machine learning. They are all this is a very ingenious concept, and the concept is so you have two density. You want to essentially measure some sort of distance between two density functions, but it's not really the Euclidean distance. Okay, so the distance is a log scale, first of all. So log scale distance, and then the evaluation should be given is at f null. So you so f1, so f1 over f0 over f1 evaluated at f1 f0. So okay, I'm not sure whether there's any other good way of explaining this concept. Anyone has a better? Oh, yeah.
So these two, it says, what does it mean by denominator measure mu?
Ah, this guy. You mean this one? Yeah. So that is actually dominating measure. So yeah, that's a good question. Actually, I should maybe it's a good time to make it clear. So this will be covered in 642, right? 641. Okay, thank you. So when I was a student, there's no 641. So anyway, so x is random variable, right? X is random variable with density f. But sometimes x can be, x can be, for example, discrete or continuous, right? So then the meaning of integration changes, right? If it's discrete, then actually the probability of, for example, x equal greater than 2 is actually means what? Summation over x probability, x is greater than something like this, right? But we still want to express it in terms of the integration. Integration over x fx d mu x. So that is kind of some convention, I should say, in probability theory. And the convention is okay. So the concept is we want to express this probability as a integration, regardless of whether it is discrete random variable or a continuous random variable. Okay. So that means the measure, the dominating measure for categorical variable makes the integration to summation, while the dominating measure for continuous variable actually make the integration as the integration in the Kullback, right? Kullback measure. So that is the basic concept, and I didn't want to distinguish the continuous variable and then a categorical variable separately. I want to express it unified way. That's why I use mu y. Sorry, sorry, I should explain it. Huh?
Can you it's in small second in the second line? There should be indicator, not quality.
This one.
In the second line,
It is this one.
is that the 8 or P? I mean, I think it's
Okay.
indicator. P.
Right. That's right. So you mean the what am I doing? I guess something like that, right? I mean,
Yeah.
P x equal to. Thank you. X. Right. Yeah. Okay. Yeah. Yeah. Feel free to ask questions. Probably it's more important actually in the beginning. I mean, beginning of the semester rather than, the middle of the semester. Probably it's too late. So it's actually have some, courage to ask questions. Okay. Yeah. Any other questions? Okay.
So the formula is fixed, like the logarithm is not different by the form.
So it's not symmetry, right? That's a good point. So one clear implication is that df0 given f1 is not equal to df1 given f0. But one important result, which is very important, is that Kullback-Leibler divergence measure is non-negative and is 0 if and only if f1 and f0 are equal. So that is actually nice property because that it gives us some similarity with the distance, the usual concept of distance, right? So distance should be positive, not negative, right? Any measure can be, if it is going to be used as a distance, it should be non-negative, first of all, no matter what, right? There's no such thing as negative distance, right? So that's good thing. And also, if the two elements are equal, then distance should be 0, which is exactly what this result is saying, right? So in that sense, this is maybe not perfect, but maybe it's okay to use this one as some sort of a tool for discussing distance between two density functions. So anyway, we'll worry about the real meaning later, but just for now, let's focus on the mathematical result. So the tool we are going to use so we keep, to keep doing this. To solve this, we need to introduce this one. And to solve this one, so to solve A, we need to introduce B. And to solve B, we need to introduce C. And sorry about that, but that is what it is. So anyway, Jensen's in. So G is a convex function. So I assume that you have probably heard about, at least heard about Jensen's inequality, but I'm gonna introduce it and do it again. So G is a convex function. Then on any random variable, we have this. Furthermore, so G of the expectation is always right. So probably so this is convex usually. So we have a 2 point, any 2 point, and then suppose you have any middle point, right? Any convex average, any point in the middle, say here. So then from here, you have this point, from here, you have this point. So average. So you can see this one is lower than this one. Okay. That is actually what this Jensen's inequality is saying, right? So the average of the 2 point in G is greater than or equal to the G of the average. Okay. So that is the Jensen's inequality. And so for strict and log is concave. Log function is concave. And so the minus log is convex. And so this minus log x is a strictly convex function. So we can apply the Jensen's inequality. So that means this is the definition. So first line is definition. And then this guy is actually Jensen's. And the last one, what is F E0? E0 is an integration, right? Integration of this quantity with the density F0. So F0 cancels, right? And then the integration is only with respect to F1. And the integration with F1, integration of F1, y d mu y is 1. Okay. And so, and then we take the log. So log 1 is 0. So we get this one. So that means that actually proves something, right? Okay. So now it's like to prove A, we introduce B. To prove B, we introduce C. Now we prove C. So then we are now in a position to prove B. And then after that, we'll come back to proving A. So we prove this one. And so we are now in a position to prove lemma 1, lemma 2.1. Okay. So the Shannon Kolmogorov information inequality, what is that? Well, yeah. I'm sorry, are you talking about this page? F1?
I mean, in the definition, the Kullback-Leibler.
Here?
Yeah, in the right side. Log of F1 by F0 or F1 by
F1
by F.
divided by F0 to have expectation equals to y now.
Oh, really? Okay. So, are you saying that the other principle has a different definition set?
No, in the next page 7, F1 divided by F0.
Ah, in the proof, okay. Here? It's okay. So you guys all know, so I'm the only one who don't know, but maybe that's not a big. So, in the proof. Okay. So, okay. Sorry, this here actually take a minus. So minus so that it okay. So where are we now? Where we want to show this. So what we know, Kullback-Leibler F0 F1 is non-negative. And this guy is actually, if you use Q theta 0 minus Q theta 1, right? I mean, if I write it as a F theta 0, this is F theta 1, right? Then by definition, the Kullback-Leibler divergence of this guy is this guy. Right? Because the Q, the definition of a Q is, so this guy is expected value of theta 0 at log Fy theta 0. And this guy is theta 0 log Fy theta 1. So So because we know that this guy is positive, I mean non-negative, so that means we have this one non-negative. That means F0, I mean Q, right? Q zeta it has a maximum at zeta null for all zeta. With equality, if and only if this is equal. Zeta 0. Zeta 0, zeta 1. I think I got somehow I cannot really check the message here. So if you have a question, you can unmute yourself and ask, okay? The Zoom. And now to show uniqueness, so the Jensen inequality actually have okay. So this is if and only if. Right. So the equality holds if F0 is equal F1 with probability 1. So that means the density is equal with probability 1, which implies the parameter, right? Two densities are equal, that means the parameters are equal by the identifiability condition. So that's why we need the identifiability condition to show uniqueness. So it's not just the zeta 0 is the maximum. Okay, so it's not just the, so if you did, let me just repeat, okay. Q zeta, Q zeta is a expectation at true parameter value, which we call zeta 0, and log density, right? So as a function of zeta. And basically this lemma, what the lemma says is that the maximum is achieved at the true parameter. Okay. And also the maximum is unique. So it's not just the maximum is achieved at zeta null. Actually, the maximum itself is unique. And you might wonder why it's a so big deal, right? Why you really spend so much time talking about the maximum of this guy? Because the answer is this one may look very weird, but actually this is just the population mean, right? This is expectation. So sample version, what is the sample version of this guy? The sample version of this guy is 1 over n, summation, I equal to 1 to n, log f, yi, and zeta. Okay. So that is what? That is actually log likelihood, right? So log likelihood. So that's actually our old friend. So that means what we keep using the log likelihood, you know, in static class 521, I mean 542, right? And now we see that this log likelihood is actually a key component, one of the key components in discussing this Kullback, has some real good connection with the Kullback-Leibler divergence measure. And yeah, actually, let me, so it's a little bit slower than I planned, but anyway, that's okay. But here's an interesting point. So P hat, I don't know whether you guys really catch this right away, but let's assume that P hat is the amplified distribution. So amplified distribution is what? You have a jump in the data point, okay? If you think of the CDF, cumulative distribution function, you have a step function in the sample, right? So this is a P hat, and P belongs to a family of distribution, parametric family, for example. Then the MLE of P can be defined as the minimizer of the Kullback-Leibler divergence measure evaluated at P hat given P. And why? This is a little bit too much to maybe a little bit beyond the scope of this class, but still, I want to just mention it quickly. So what is this? This guy is by definition. So let me use the definition first. Okay, log P hat X or Y, right? And P set up X. And then P hat X P B. Right? And then see if you write, what is this? This is log P hat X times P hat X P mu X minus log P theta X P hat X P. And now we are going to look at as a function of theta. So if you view it as a function of theta, this is just a constant. Right? This is free of theta. And this guy, what is this guy? This guy is logarithmic. Because P hat is just the amplified distribution. So integration with respect to P hat is just the sample version. Sample version of the expectation, right? So this is actually this guy. Okay, so this is what? This is our old friend, logarithm. So that means the meaning of the MLE is a minimizer of the Kullback-Leibler divergence measure from the amplified distribution to the model. To the model space. Okay. Well, so I have I recorded. You know that I recorded this, and also I have a script, and also I upload the textbook file to the Canvas. So I hope that these three combination give you some at least some resources to catch up. Okay, if you cannot really fully digest in the class, but still, I hope that you can catch up. So I think I covered this, right? And now, so okay. I just mentioned this, right? So on the identifiability, this guy is unique maximum at zeta null. And then second point is that I have a Qn, which is actually logarithmic, right? Logarithmic. So you can see that this one is a sample version of Q zeta, right? So we know the law of large numbers, Q zeta will converge to Qn zeta will converge to Q zeta pointwise. So for each zeta, so you might wonder, okay, where it's like this, okay. Here's a sum, Q zeta, right? And we know that the maximizer of Q zeta is a true parameter, which is our parameter of interest. But we don't observe this one, right? We don't observe from the data. What we observe is a sample version of Q zeta, which is Qn. So Qn zeta is a sample version. So that could be maybe something like this. Right? Could be something like this. So if I have n is large, what I know is that it will be very close to the true Q function, right? So that we know. And so by the way, the maximizer here is here. You have zeta at n. Right? So the main thing is that, well, maybe this Qn zeta is very close to Q zeta anyway for substance large n. So then that means, can we say that zeta hat n will be very close to zeta null, right? So that is our hope, right? And so that is the statistical problem, and the answer is that's not enough, right? We need a more stronger condition than just the convergence, and that's this theorem is about. So the theorem is that it's not just the pointwise convergence. The convergence should be uniform. The uniform convergence means that the convergence, so what do you mean by non-uniform? Non-uniform means that for each different point in the certain epsilon level, we may require different n, right? So we need, so for example, here, maybe sample size 100 is enough within certain boundary. But here, sample size should be 1,000, for example. That's not good, right? So then that means the closeness changes with the different sample size. So that, and so that's not what we are talking about here. Uniform means that overall, throughout throughout this zeta space, we can control the convergence usually by picking a single sample size. So above that, it's okay, something like that. And second one, uniquely maximized at, so then that is actually we already covered. So second part is already covered. So under these two conditions, recurrence will be satisfied, and that's not really the proving this one is not really the focus of our class. So I will I'm not going to cover it, but I just put it in the script just for if you guys are interested, you can check. So the definition of the convergence property is this one, right? So the property that zeta is outside the certain epsilon range from the true from the truth, the probability goes to 0 as n goes to infinity. So if set parameter model is not identifiable, then that means what? That means two different parameters can determine the same, right? And then it may not converge to a single point. So if non-identifiable, sometimes we could get confused and just apply use the non-identifiable model and compute the MLE. For MLE, in that case, the MLE may have some numerical problem. So basically, it's like if the likelihood is flat, I mean, right? I mean, if it's non-identifiable, so you may have a very flat like then the maximum is just the random variation, right? You sample size. Okay. Last question is, if the true distribution does not belong to class P, which point does set the height commute to? Anyone can answer this question. So we know. So the theory here is what? MLE converges to the true point. But if the model is wrong, what I mean by true model, right? So the model space we are considering is here, but the data is actually generated from outside the space. Okay, suppose. Then how this big law of large number changes. So that is something that you can think about. I think I can give you an answer shortly, but let me stop share for now and stop